Hey everyone, Mr. Evans here with your pre-recorded lesson on Unit 7, Lesson 9, Transitional Fossils.
We are all probably familiar with what a fossil is. A fossil is a mineralized bone or partial skeleton, or in rare cases, a complete skeleton of an animal that is more than likely now extinct. Um, Fossils can tell us a lot about what how an animal lived, its behaviors, when it lived, where it lived, can tell us a lot of information, and the more complete of a skeleton one is able to find, the more information you can glean from that skeleton. We've been talking about how species change very, very slowly over the years to better fit and survive in their environments. And when you introduce enough changes over a very long amount of time, that actually can lead to speciation. Imagine just moving very slowly into a different form over generations. The offspring is a little bit different, then their offspring is a little bit different, then their offspring is a little bit different, with teeny tiny changes being introduced over huge spans of time. Now, no human ever live long enough to watch these changes happen. It happens in spans that are way outside of our lifetime. So it's not possible to watch it happening in real time with higher organisms, with larger, more complex organisms. Um, People have seen it happen with, bacteria, and even to a smaller degree, something like fruit flies that have a really short lifespan. But for organisms that have longer lifespans, you just can't watch it happen. So you have to find evidence that it's happening, and you have to look for evidence, and you have to put together the pieces of the puzzle over the past millions of years. And one of those pieces of evidence is fossils, transitional fossils. Because if a species is changing, over generations, you can find fossils of those species, and you can actually see the changes that happen in their skeletal structures. One of the kind of basic rules of geology is the deeper you dig, the older the stuff that is in that layer of rock and dirt is. So if you find a fossil that is buried deep underground, you can kind of assign a year to that layer. If you dig, 10,000, 1,000 feet down, then maybe that's 10 million years ago. If you dig 500 feet down, that's 500 million years ago. That's 5 million years ago. So as you get closer to the surface, that means that animal died more recently. Makes sense, right? I mean, something dies, it gets buried, erosion and sand and the water kind of piles on top of it, and it makes a deeper layer over time. So you can use this as kind of a clock to determine when this animal was alive, and you can look for fossils that are similar but a little bit different. And you can kind of see how the changes happen over the years, if you're lucky enough to find the right fossils. And we still haven't found all of the fossils, and we never will. But we have found enough to start putting together a picture of how these species evolve and change over time. Now, the picture on the screen here has four very different species. We've got a dolphin, we've got humans, we've got a horse, and we've got a bat. They're all very different. You look at them. But if you look at their skeletal structures, you see similarities. These are their limbs. Dolphins have fins, humans have arms, horses have legs. Well, humans have legs too, but horses have legs. Bats have wings. If you look at the skeletons, you can see that they're kind of set up similarly. You have like a base here. You have two bones providing like a hinge support. You have these little bones here acting like kind of ball bearings, so you can move the limb around. And then you have phalanges that come out and extend and allow other things to happen. It's the same basic setup across all four of these species. The lengths and the widths and the shape differ a little bit, but the basic setup is the same. Base bone, two, uh, two bones that kind of act like a hinge mechanism. So you got some ball bearings here, and you have the phalanges coming out. Phalanges is a fancy word for fingers. Um, Even in the dolphin, I mean, it doesn't look like they're separate on the outside of the fin, but if you look inside the fin and go to the bone structure, you can see these phalanges, and they kind of look like fingers. Um, on the inside, the skeletal structure is the same, even though they don't like separate out on the outside like fingers do. But this is evidence that all of these species, even though they look very different, they're coming from the same basic plan, the same basic skeletal plan, and over many, many millions of years, they diverged, they changed, they became fit for different environments. But this shows a relationship that at some point they were all coming from the same origin source. Now you have to go back pretty far to find the origin source, the common ancestor. You're going to hear that word coming up here in the next unit or two. You're going to have to go back pretty far to find the common ancestor for all these different species. But they're all coming from the same base plan. And then they changed and diverged and split off over really, really long periods of time. So that's all fine and good. I mean, you can say, yeah, skeletal structures are the same, but maybe that's just because, it works. It's a basic plan, it's a functional design. I mean, you don't reinvent the wheel. So what's some more proof that we have that a species can actually evolve into a completely new species over a long period of time? One of the most fascinating examples of this is with whales, because I think that is like one of the most impactful examples of how a species can just completely change based on its environment. So there's an image on the screen here, and none, with the exception of this last one at the bottom, Odontocetes, which is a modern day dolphin, none of these species up here exist today. They're all extinct. But fossils have been found for all of these critters, fossilized remains. And dolphins and whales are mammals. You probably all know that. You probably all learned that in third grade. Dolphins and whales are mammals. They breathe air, but they live in the ocean. Why would something that lives in the ocean breathe air? I mean, most of the other stuff that lives in the ocean have gills. They can breathe the water. They can extract oxygen from the water. That seems like that is the best adaptation to have if you live in the water. Why should you have to come up for air if you live in the water? Well, most of the other stuff in the ocean, it follows that rule. Most of the stuff that lives in the ocean have gills. They can breathe in the water just fine. Dolphins, porpoises, whales, a few other things, they have to come up for air. They have lungs like we do. They don't have gills. They can suffocate. They can drown. They have to come up for air. Well, how does that happen? Why? Why are they different? What's weird about them? Well, long, long, long time ago, dolphins, whales, those kinds of seagoing mammals, they lived on the land. They were a land species. They breathed air. They had lungs. They walked around on the land. And it was this guy right here, Pachyceti. I don't know if I'm saying that right. But it's, this critter right here kind of looks like a funny looking fox. Well, they realized that if they lived near the shoreline and they just kind of went into the water a little bit, they could find food that was not accessible to their competition. Mussels, crabs, scallops, all the stuff that kind of lives in the shoreline. They kind of just started dipping their feet back in the ocean. Hey, there's food in there and no one else is getting it, so I'm going to go get it. That gave them a competitive advantage. Now, that could have been caused by some kind of mutation in their brain that said, hey, I'm not afraid of the water. I'm going to just kind of peek in there and see what's up. Maybe it was a behavior that was demonstrated by one and the rest of them just kind of followed suit. Who knows? But for whatever reason, they started dipping their feet into the ocean. These guys right here, these Pachycetides. Well, once that happened, anything that allowed them to do better in the ocean, whether it was like webs between their toes or their noses were a little longer and they could stick them up above the surface of the water while they were sticking their head under scouting for food, those traits became survival advantages. Being able to survive while you're dipping into the ocean looking for food became an encouraged trait because you could find food better, you could spend more time in the water. So those individuals were able to survive and reproduce better than ones who couldn't. And the traits for the water adaptation continued on down the generations until you get ambulosity. And I don't know if I'm saying that right, but it don't matter. But you can see this guy here, he's got some webbing between his toes, his snout's a little bit longer. He's starting to kind of look like a funny crocodile, right? He's getting sleeker and longer. These traits over the generations are being encouraged upon. Go a few million more years down the line. Now they're like longer and sleeker. They got these long noses here that allow them to grab fish, maybe stick their noses above the surface of the water to breathe without actually having to come up all the way. They still have legs and limbs here, but they're not really totally functional for walking on the land anymore. Maybe they can kind of crawl around and drag themselves around the land if they need to, but it's not really their primary function. They're kind of going away. And you can move on down through the ages and see how where we started here and aquatic traits are encouraged because they help the animal survive in an aquatic environment are encouraged until we get down to the dolphin. Now, you might ask yourself, why didn't they just evolve gills? Why do they still have lungs? And here's the reason. When you are talking about exterior features, okay, limbs, teeth, those are generally easier to evolve because it's just an affect. It's an exterior affect. There's not any downside at all to having your limbs adapt to fit an environment. So it is easier to encourage those traits in terms of survival because it is very rare there is any kind of energy trade-off or like any drawback. It's something that happens more naturally, more regularly. It's like more obvious. It's easier to encourage a trait in body shape and limb shape. There's less pay up. There's less, what's the word? The animal doesn't have to give up like hardly anything. But when you start talking about evolving biochemical functions, organ functions, something that's like very basic to the organism, that they literally depend on for life, that becomes a trickier game. Like if finger shape changes, if leg shape changes, a little bit, that's not going to threaten the life of the animal. It's nothing that is going to have a huge impact right away. The small change is fine. But when you start messing with biological function, like how the animal takes in oxygen, that becomes a much trickier business. Now, I know that's kind of weird to explain, but think of it as like having a house and changing your wallpaper versus tearing up your foundation. You know, you can change the wallpaper, you can change the paint, you can change the carpet, but when you start talking about getting into the walls and ripping out the plumbing, that's a bigger deal. Okay, it's the same thing with basic functions like organs, oxygen, blood, heart. Much harder, much longer period of time to have those things evolve. Now, in 50 million years, maybe dolphins will have gills. Who knows? This is still a relatively new evolutionary change. I mean, these are mammals. These things right here, they lived after the dinosaurs went extinct. These guys were around after the dinosaurs went extinct. So we're talking evolutionary change within the last, 20, 30 million years or so, which is a long time, but evolutionarily, it's not like a ridiculously long time. That's not enough time to change basic function. So that's why dolphins don't have gills yet. But given enough time, if it's a survival advantage for them to have gills, maybe they will evolve gills given enough time. So all the skeletons of all these transitional species have been found um, near shorelines, in the ocean, underwater, in places where there used to be oceans. Maybe some of you have heard that Nevada used to be under Lake Lahontan, like most of the state was under Lake Lahontan. It was we're living at the bottom of an ancient seabed right now. So all these fossils have been found, and you can put them together side by side and say, wow, look at all these changes that have happened. And the other thing is, it is very possible that at some point, fossils will be found for the species in between here. Maybe there was, this guy right here, significantly different from this guy. Maybe there's a fossil that will be found in here at some point that shows another transitionary form. Who knows? It's out there. The cool thing is that before people really started discovering fossils in a big way, they were predicting we're going to find fossils that show these transitionary forms between animals. And guess what? They did. So that's an example of a prediction that science made that came true. And that's the whole point of science, is trying to make predictions that come true.